Yeah, so I suppose what I'm doing is kind of following on a little bit from providing hopefully a bit of a link between some of the palaeoecology and some of the archaeology that's going to be coming, and also looking at how potentially we can start to think about using these different data sets together. And I'm using chronology really as a way that we might want to think about doing that. So we start off with, we have some archaeology data, we have some palaeoecological data, and we really want them to overlap. But in some areas they overlap quite nicely, and in other areas they really don't. So how can we actually start to get around that? And I suppose the crux of what I'm arguing for really is that we need to understand the complexity of the data that we're dealing with before we can start to move forward with that. So if we look at archaeological data, we might have some very discrete deposits in time that these might represent different settlements. With a palaeoecological record, potentially we have a long time depth going right the way back. We also have historical data, and I suppose within that I'm also including kind of ethnographic and some oral history data too. But also within all of this, we have a very much of a kind of temporal nature. So we might not know when some of these archaeological periods or one of these archaeological episodes actually happens. We might have a date for one of them, and we might infer that from something else and apply that to another one. Within the palaeoecological record, we might have 3 or 4 radiocarbon dates, but then there might be gaps in that record. There might have been periods of hiatus, so we might have bits that are missing. But equally, we might really be interested in where these points occur for which we don't actually have any dates. And then added to that as well, we obviously have the historical records, which are very kind of discrete points in time. We also have the spatial distribution, so again, they're not all necessarily going to be in the same place. We've got all of these data sets, we think they all ought to combine, but how do we combine them? Within our data sets as well, we have different issues too. So if you look at the red dots here, if you take red to be local, an archaeological site could be very, very local in nature, whereas the local signal in a palaeoecological record could vary, but that might not be so local. The area around each site might be represented kind of equally in both records. And then the regional record within a palaeoecological site, for instance, that grey, it could be very large if you've got a lot of windblown pollen coming in. But for an archaeological site, unless there's something perhaps like long distance trade happening, you might not get a very large regional sequence. So we have all of this kind of complexity to be thinking about. And why is this important? Well, part of interdisciplinary concerns, especially trying to integrate palaeoecological records and archaeological records, really since the 1990s, have been trying to integrate these. And some people have been doing it successfully and others less so, but it's something that we're still kind of, I think, grappling with a lot. Within my role, I'm looking at bringing data sets together for 2 reasons. One is the wider work of something called Land Cover 6K and Land Use 6K, for actually trying to understand how archaeological and palaeoecological data can provide information over the last 6,000 years for land cover and land use. But I suppose what I'm saying is before we can bring those data sets together, we need to really understand what they're doing and how they may or may not link. And secondly, if we want to take some of this stuff into the future and actually try and make it relevant to things like policy, we need to understand that complexity, but we also need to simplify it and be able to put it across in a way that is understandable to other people as well. So I'm starting to use radiocarbon dating and particularly Bayesian modelling to try and bring these things together and try and provide some of these links between the different data sets. And that's what I'm going to explain to you this afternoon. So I'm looking at an area around Engaruka, which is going to be introduced later by Carol. So I'm not going to say very much about that because that will come up in a minute. But it's looking in North Tanzania, and Engaruka is where the green dot is. I'm also going to be looking at a couple of palaeoecological records, one from Lake Emeka, which is about 15-20 kilometres away, and another from down here as well. Okay, so coming back to this idea of the palaeoecological sequence, where we have dates from within a certain point in a core, but we actually want to know when other events were happening. It doesn't really matter how high a resolution our palaeoenvironmental records are, unless we've got a robust chronology that goes alongside it. Effectively, what we're trying to do is just pin the tail on the donkey. So it's how can we do that in a way that actually works? In the past, we've had very simple age depth models which have been created, where we've literally taken 2 dots and with a ruler you join them together. And then in theory, you can read off a nice date from that. Now, this has moved on a lot within palaeoecology, and that there are now more sophisticated ways in creating these models. But we still need to kind of go back to understand that what we're trying to do is go really kind of beyond that. The Bayesian method is basically taking the point that a radiocarbon date isn't a date, it isn't a calendar date, it isn't a point in time. It's actually a probability distribution. So if you have a look at, where are we? Let's put one here. The light grey represents what a radiocarbon date would have been. The dark grey showing what it's going to be when it's finally modelled. But if you can look, this age depth model, it's still got time along the bottom, depth going up the side. But what it's doing is it's flexing, it's getting bigger and wider based on the radiocarbon curve, which isn't just a straight line, but does also do different things as well. So what you're doing is you're not getting necessarily a very precise date, but you're getting one that is more statistically robust at the end of the day. The other point, so we have radiocarbon dates that we can model, which are all of these ones here in black, but also I can say, right, well, I know from the pollen diagram for this site at, 19 centimetres, we've got a massive change in Palaeoecology, for instance, in grasses. And when that change occurs, it's likely to be representing something that's happening, for instance, in the region or something that's site-specific. And I can ask it to give me an estimate for that date. And that estimate is represented by that little black band there. And so again, we can do the same thing here, and this is for Lomwe as well, where we've got dates, but you can see this top one doesn't fit in, because what this type of modelling can also do is it's a model. It can say, well, actually, I think, based on the data that you've given me, that this is actually an outlier. So other different types of programs will do this in different ways, but it means that it can still construct a model, so you can still use the dates that you have, but it's excluded the one that is likely to be out of sequence. I'm not going into how you choose your samples and all of those things. That's kind of an entirely different talk as to why that might be out of sequence. The other powerful thing you can do, and this is where actually you start to bring in other disciplines, is this little top date here, the one in red. That's actually based on historical data. So I don't just have to put in radiocarbon dates. If we've got other information that we can use, then we can put that in as well. So this is a historical date from the 1900s, where we know that exotic trees were starting to be grown and produced, and so therefore the pollen signal from those in this paper has suggested that spike in those pollen grains comes in at about the 1900s. And what this does is it actually also just means that we can then start to read off other things from this curve too. So I've chosen in the pollen sequence where there's potentially kind of an area of colluviation, so there's a change in what's happening in the environment, to say, well, okay, when does that colluviation happen? Give me a start date and an estimate for an end date as well. So it's not just a case of creating an age depth model, it's actually being able to interrogate it in a way to ask questions of other types of data sets as well. So we can also do this for the archaeological data as well, not just for palaeoecological data. And Bayesian modelling for archaeological dates is becoming increasingly commonplace. So this middle block here of big dates is from the south village at Engaruka, from work that was done in the past. We don't necessarily know the stratigraphic order of these dates, so that's why they've just been put into a phase. I haven't said I think this date comes before this one, it's just literally been put in as a phase. But what I do know is after that phase, we have European settlement, or we have European accounts to say that basically that site had gone by the mid-1800s. So we can use that date to help constrain the dates lower down, because even though the radiocarbon dates, which remember the bits in light grey, potentially carry on right the way into the 1800s, we know from the historical data that that can't be true. So the model takes that into account, which gives you a narrower predictive range. So we can start to have a look at when this boundary end is giving you an idea of when the settlement might have come to an end. So again, what we're doing is using the archaeological data and the historical data there together. So to go back to the palaeoecological data, so I had the change here which I wanted to model, which is saying that we had less woodland and we became a more kind of open savanna type of an environment after this point. What I'm actually trying to do is we can take that and then model this in more simplistic terms, because these diagrams are not easily explainable, and they're not something that you want to take out to the public in any way, shape or form. And even within a scientific audience, you quite often get glazed looks as soon as they go up. So by simplifying it into a band, we have the blue band, we're saying kind of beforehand we have woodland, and then we have a green band where we have perhaps more an open time. But by gradiating it, rather than saying it changed at this point in time, we're kind of showing that there is some complexity in there, that it changed within that band. And then we can start to do this for the archaeological sites as well. So this is that same band, but now put upright. And again, you've got the years down the side. So we can see that we've got a change here from forest, savanna, grassland into just savanna grassland. We then look at this curve over here. This is doing the same thing for the archaeological data, where again, we don't really know what happened in the red period with Engaruka. There may have been something there, there may not have been, but we know the site roughly came into existence around this same period. And Engaruka is settlement, but it's also a highly irrigated landscape as well. And likewise, we know the settlement kind of finished at this point. So we can start to look across and see if there are any comparisons. And what we can start to do is we can build this up with other types of data. We can build it up with different types of questions. And it's just a simplified way of being able to present the data together. So what I'm suggesting that we can do by using this is actually starting to put the historical data with the archaeological data, with the palaeoecological data. We can also start to estimate when these stars occur, and so that we can look across and actually try to see how they may or may not link with the archaeology. So in summary, and this has been a rather whistle-stop tour, and I've got a feeling this is nowhere near 15 minutes, catch up some time. The Bayesian modelling actually allows us to combine different types of methods from across disciplines, but within a single model, like those little ones that I showed you. But also we can use it more in a summary format as well. When we start to produce those summary diagrams, we can then start to look at different events. There's problems with this term events and whether they actually exist, but that's again another talk. And also they are a lot more palatable and a lot more understandable to a non-specialist audience as well. So thank you very much.